Hey, this is Charlie Thompson, and I wanted to do an intro video to the intro video for the chapter on climate change. So, science. This is a science class, and as part of a science class, I thought I wanted to talk about how do we know what we know? It's way, way, way important and way bigger a topic than I'm going to cover today, but it's something that's important to think about. How do you know what you know? So the answer is, in science, we use the scientific method. The scientific method is it's how scientists know what we know is true. So you start with a question that you want answered. You come up with a question, you think about some reasons why that might be happening or not happening. And then you start to think about, well, how could I test that? Because if you want to use the scientific method on something, it has to be testable. You have to be able to test it. You have to be able to write up how you tested it so that other people can test it. And we see if they get the same results as you did. That's an important part. It's that the tests have to be repeatable. And they have to be provable. You have to come up at the end of the experiment. You either have to have proven or disproven whatever it is that you're looking at. So let's look at an example of the scientific method on something that's testable. Is Earth spherical? So is that something that we could test? Yeah, we could make a prediction. In fact, here we go. If Earth is a sphere, people at different latitudes and longitudes should see the sun at an angle that's relative to their latitude and longitude. So the angle of the sun that you see should be different from the angle of the sun that somebody else in a different location sees, and the difference in the angle of the sun should be a function of how far apart you are. So how could we test this? Well, here's a north, this is the North Pole right here. Where'd my turn on the laser pointer? I'm glad the cat isn't in the room. So here's the North Pole at the outside. I don't know, it might be like 40 degrees, 50 degrees, probably closer to 50 degrees. That's probably 60 degrees. Anyway, here's the North Pole. We're looking towards the equator. So if Earth is a sphere, then at the same exact time, all over the world, people should be seeing the sun at a different angle over the horizon as a function of time of day. So my prediction would be that we're just going to say the sun's over here, shining someplace in Eastern Europe over Russia. And so this half of the globe should be dark. This half of the globe should be light if it is indeed a sphere. And at this location, the sun should be directly over the horizon. This should be 2 hours later, 4 hours later, 6 hours later, the sun should be just setting. And here the sun would just be, I got that. No, that's right. Sun is rising. It's 2 hours later, it's 4 hours later, 6 hours later, it's noon. It's 2 o'clock in the afternoon, 4 o'clock in the afternoon, 6 o'clock in the evening, and the sun is just setting. So is that something that we could test? Yeah. The Flat Earth Society, ironically, says that they have members all over the globe. I don't know if they knew what they were actually saying. So they could call their members and on the same time have them go outside and just snap a picture of the angle of the sun over the horizon. You know, what time is it? If it's a different time, then that would confirm that Earth is spherical. Okay, got another one. Same idea, because Earth is spherical both when you look at it from the top and from the side. So on the same day, at the same time, people at different latitudes should see the sun at a different angle above the horizon. So this image that I've picked, it's on the summer solstice, the June solstice. The sun is hitting the Tropic of Cancer, 23.5 degrees, and the angle of the sun over the horizon should be a 90-degree angle. If you move 23.5 degrees away, the sun should be 23.5 degrees away from 90 degrees over the horizon. And as you keep moving away, it should be 47 degrees away from 90. And at the Antarctic Circle and Arctic and Antarctic circles, the angle of the sun should be parallel to the ground at the same time. So again, all you got to do is call up the members of the Flat Earth Society that are at these different latitudes at noon and have them go out, snap a picture of the sun. If the angle of the sun is at different angles to the horizon at different latitudes, and if the relationship between the angle of the sun is the same as the relationship of that latitude to the subsolar point, then Earth is spherical. Okay, so there's an example of a testable experiment that you could perform. I want to move on and talk about the scientific method in the context of climate change. So the first question we got to ask is Earth warming? So is that something that we could test, something that we could measure? Yes. And Earth seems to be warming unless all the thermometers on Earth are lying. So option A, here we've got from 1880 to the present, we have a continuous record of temperatures measured by temperatures. We've got records of temperature going back 800,000 years. This is a very short-term record, only going back 1,000 years. You can see the overall trend was kind of cooling right up to the Industrial Revolution when we started burning fossil fuels in a big way. And then the temperature has rapidly jumped up. So from the Industrial Revolution to the present, over the last 200 years, the temperature has gone up by a degree, which is considerably more than any other temperature movement over the last 1,000 years, which would seem to be important. So I think this answers the question is Earth warming? Yes, Earth is warming. Okay, so why is Earth warming? And I can only come up with two reasons why Earth would be getting warmer. Reason one is we're getting more energy from the sun. So either more energy is, because we know it's warming, either more energy is coming in from the sun, or something is trapping that heat, making the Earth warmer and warmer and warmer. So either we're getting more energy from the sun, or something is keeping the heat from leaving. More of the energy is sticking around. If it left, Earth would be cooler. If it sticks around, Earth gets warmer. So let's take a look at question one. Are we getting more energy from the sun? No. So here we've got 1860 to the present. This is solar irradiance. This is the energy released by the sun. Recorded in watts, which is just a unit of energy, watts per square meter. Square meter is about a square yard. So this is about enough energy to run a hairdryer, assuming that it's all 1366 watts get converted to electricity. That's enough to run a hairdryer off of the light striking a square yard at the top of the atmosphere. So it's gone up by, I don't know, half a watt out of 1300 watts. Which would be 1 over 2,500. Yeah, it's an incredibly tiny amount. So it might have gone up by half a watt, maybe, out of 1,300 watts. And let's see if the rise in insolation of a half a watt, if that corresponds with the rise in temperature. So here we've got the blue lines are the blue to red. Are the temperatures cooler or warmer? If they're red, they're warmer. If they're blue, they're cooler relative to the whole 20th century average. So it looks like from 1960 to 2000, the amount of energy coming in from the sun was about the same. And from 1960 to 2000, we have recorded the warmest decade ever, which beat the record of this decade, which beat the record of this decade, which beat the record of this decade. Every decade for the last 4 decades has been the hottest decade ever recorded on Earth. 2016 was, I believe, tied with 2020 for the warmest year ever recorded. So temperature's gone way up at a time when solar energy was flat. So no, it's not necessarily that we're getting more energy from the sun. Scientists have looked at all of that. But this gray line is carbon dioxide, and carbon dioxide absorbs heat in the atmosphere. In fact, carbon dioxide is the most important element of the atmosphere that absorbs heat. And carbon dioxide in the atmosphere has gone from about 290 parts per million to about 414 parts per million. Humans have never been alive at a time when there was this much carbon dioxide in the atmosphere. So let's look at the last 800,000 years of blue is carbon dioxide, red is temperature. You can see there's this 100,000 year trend, 10,000 years of warm, 90,000 years of cold, 10,000 warm, 90 cold, 10,000 warm, 90 cold, 10,000 warm, 90 cold, 10,000 warm, and warmer and warmer and warmer. So carbon dioxide has gone between about 280 to 380, 280 or 280 to 300. Sorry, let's start over. 180 to 280, 180 to 300, 180 to 417. So carbon dioxide, as carbon dioxide goes up in the atmosphere, it absorbs heat, which warms the planet. It's pretty much that simple. It's fossil fuels. Yes, scientists are well aware that there are natural cycles where Earth's climate changes. Those are the same people that telling you this isn't a natural cycle. This isn't part of this 100,000 year cycle of 10,000 years of warm and 90,000 years of cold. So here is carbon dioxide, 417. I'll just say it again. I think we haven't seen levels of carbon dioxide this high on Earth in the last 30 million years. The last time there was this much carbon dioxide in the atmosphere, so much ice had melted and Earth was so much warmer that there were tropical swamps and alligators in New York, which it's entirely possible that's the future that we're headed to unless we do something really quickly. This is evidence for climate change, and I wanted to talk about the difference between predictions, like using computer models to say this is what we think is going to happen. These are all things that we've recorded. These are, if you're denying these, you're denying what you're seeing with your own eyes. We could make a list of everything that we would predict. If climate's changing, what would you expect if the atmosphere and Earth is warming? Well, melting glacial ice, check. 95% of alpine glaciers are in retreat. Greenland and Antarctica are melting extremely rapidly. Higher temperatures over the land, yes. Reduced snow cover, yes. Higher air temperature over the ocean, yes. Higher temperature over land and the ocean, yes. Higher sea surface temperature, yes. Higher heat content in the ocean, yes. Higher air temperature in the lower troposphere, yes. More water vapor in the atmosphere? Yes. This is related to the record snowfall that just hit Cheyenne, Wyoming. I think they just beat their all-time record for 24 hours of snow. How can that be if the climate's getting warmer? Well, as the atmosphere gets warmer, you can have more water vapor, so you've got more water vapor to condense and fall as snow. So by every conceivable measure, yes, the climate is changing. And again, these are observations. These are not predictions. These are some of the ways that we know about past climate. I'm not talking about that. I'm not talking about ancient climates, hundreds of thousands to millions of years ago. I'm talking about right now. This is what we're seeing. So this is what we're seeing. And finally, this is the average 2020 temperature compared with the average from 1880 to 1930. So Earth is about 1.25 degrees warmer Celsius, 1.25 Celsius degrees warmer. And you can see that there's an overall trend of very little change. In fact, zero. Zero change over the equator. North America has warmed 1 to 2 degrees since 1880, 1930. And the Arctic has warmed 4 to 6 degrees. So the Arctic is warming just about twice as fast as the planet is as a whole. And the only part of the ocean really that's seeing anything significantly different, or the only part of Earth that is significantly cooler, is this blob in the North Atlantic, and that's cold because of all the melted ice water that's rushing off of Greenland as the Greenland ice sheet melts. So there you have it. Earth's hotter. It's because we're burning fossil fuels. We've known since the 1800s that this is what was happening. Yeah, there's your intro to climate change. I hope you enjoy this chapter as much as you can. If you have any questions, please let me know. I love to talk about climate change.